Fuzzy Lyapunov controller, computing with words. This is the lecture 4 of this module 4 on fuzzy control. As I said in the last class, that given the Mamdani type of fuzzy logic controller, the membership functions are optimized using genetic algorithms. But the most important aspect of Mamdani type of controller is to generate a proper rule base. Here, of course, you can also generate rule base using genetic algorithm, but today we will be learning how to generate a rule base using the concept of Lyapunov function. Okay. So, this is the topic today, fuzzy Lyapunov controller computing with words. Topics to be covered today: classical Lyapunov synthesis, fuzzy Lyapunov synthesis, rotational proof mass actuator system. This is a physical system on which we will be testing our algorithm. Construction of rule base for RTAC, the short form is RTAC here, RTAC using fuzzy Lyapunov synthesis, regulation problem, controller design for regulation, construction of rule base for RTAC using fuzzy Lyapunov synthesis, tracking problem, controller design for tracking, and finally simulation results. Fuzzy Lyapunov synthesis and introduction. The classical Lyapunov synthesis method is extended to the domain of computing with words. Classical Lyapunov synthesis method is extended to the domain of computing with words. This new approach is used to design fuzzy controller. Assuming minimal knowledge about the plant to be controlled, the proposed method enables us to systematically derive the fuzzy rules that constitute the rule base of the controller. So, the objective is in this method, how do we obtain fuzzy rule base given the system, some a priori knowledge of the system or approximate model of the system. How do we generate a rule base? This approach is demonstrated by designing Mamdani type and Takagi-Sugen type fuzzy controller for nonlinear plants. The most difficult aspect in the design of fuzzy controller is the construction of the rule base. Fuzzy Lyapunov synthesis is based on extending the classical Lyapunov synthesis method to the design of fuzzy controllers. It enables to systematically derive the fuzzy rule base. Based on classical Lyapunov synthesis method, we construct a Lyapunov function candidate V and then determine the conditions required to make it a Lyapunov function of the closed loop system. Since we assume fuzzy knowledge about the plant to be controlled, the derived conditions can be stated as fuzzy if then rules. So, now let us go to the system description. Consider the following single input single output system: x dot equal to f x u, y is h x u, where f and h are nonlinear functions. Okay. So, f is this is an n dimensional state space. So, f is an n dimensional vector and u and y, they are the input and outputs of the system respectively. X n dimensional system, x 1, this is x 1, x 1, x 2 until x n. R n is the state vector of the system. The control objective is to stabilize the system around some operating point x naught. Without loss of generality, we may assume x naught equal to 0. So, Lyapunov stability theory, which we have been talking again and again, I am just revisiting that. The system x dot equal to f x u is Lyapunov stable around the operating point x equal to 0 if there exists a continuously differentiable function V x, which is known as Lyapunov function, such that the following requirements are met. V x is positive definite in the neighborhood of 0, and v dot x is negative definite in the neighborhood of 0. If you can ensure that, then the system is Lyapunov stable. So, fuzzy Lyapunov synthesis assume that the exact system model is unknown, but we do have some partial fuzzy knowledge about the system. As in classical case, we consider a Lyapunov function candidate v, derive an expression for its derivative, and then obtain the fuzzy rule base for the control input u, so that v dot is negative definite. Based on the rule base, a fuzzy controller u is obtained using general inference mechanism and defuzzification method. So, what is the objective here is that we prescribe a Lyapunov function for the system, and then we construct find the rate derivative of this Lyapunov function, put the substitute the dynamics of the system in that, and now we create a rule base in such a way this Lyapunov function is qualitatively negative definite, not quantitatively. So, what is fuzzy Lyapunov synthesis is we are using a notion qualitative negative definite. Of v dot. This is the difference, qualitative negative definiteness of v dot instead of a quantitative negative. The actual Lyapunov function approach to test the stability of a system is to find quantitatively v dot is negative definite, but now we are talking about a concept called qualitatively, if we can make v dot to be negative definite. So, FLC structures the rule base. So, normal we have two kinds of, we can have for any fuzzy logic controller of Mamdani type, we can have two categories of fuzzy rule base. The representation one is if x1 is a1 and or x2 is a2 and or xn is an, then u is b, where ai's and b are linguistic variables large or small. So, x1, x2 and xn, they are either state variables or error also, error in state variables. Representation 2 is if x1 is a1 and or x2 is a2 and so on, or xn is an, then u is a definite function. Here the b, u is b, b was a fuzzy linguistic variable, where in the second representation u is an exact function, u is f x1 x2 xn, where f is a linear function. This can be also nonlinear function, f can be also linear function anyway. Normally it is a linear function. Okay. So, fuzzy Lyapunov synthesis motivation. What is the motivation here? In a general fuzzy logic controller, the control problem is to design a fuzzy controller using information based on some physical intuition, even if the exact system dynamics is not known. But the main problem is constructing the rule base for the controller. Rule base is obtained using the notion of classical PD or PID controller in general for Mamdani type of fuzzy logic controller. But in fuzzy Lyapunov synthesis, the rule base is obtained using the notion of Lyapunov stability. So, this is the prime motivation. I can tell you how normally we do a fuzzy rule base. If this is my a general characteristic of a second order system. So, what I would like when I describe this response, this is my t, this is my y, okay, my output. So, you see that if I am here at this zone, so at this zone I can say error at this zone is very large. So, I would like when I am here, I should come very fast to this line, which is my desired command signal 1.0. So, what I will say, when my error is small and the derivative of error, the rate of change in error is either small or large, whatever it is. When it is small, I would like it to come fast. So, my controller must be very large, right. So, I can write for this kind of PD or PID type of controller, the rule bus is if E is small, E is small in this zone and E dot is small or large, then U is large. Okay, by simple common sense I can write. Similarly, if I say E is small here and if E is small, that means this zone, and E dot is also small, then U is small, because I have already reached almost I am reaching the I am reaching the set point. But if E is small and E dot is large, so obviously I must reduce the control action now. So, that is in that case I have to say U is negative small instead of positive small. So, like that the normal rule base is done in case of PD or PID type of controller. But today we will see a very systematic method of generating rule base. So, actually this entire class today is to let you know or we will learn how to generate this rule base systematically using Lyapunov stability theory. So, before that I will just explain to you one physical system that on which we will be applying this thing. This is called rotational translational proof mass actuator. You can easily see this is my rigid surface to which a cart is bound using a spring, and inside the cart there is a pendulum which rotate by the action of a torque N. The pendulum link length is L, okay, and there is an external disturbance F that is applied on the cart. See, the objective is to control this pendulum the way we like. Okay. I may like to keep this pendulum at an angle theta or vertically downward, vertically upward, whatever is the desired thing, or it has to follow certain trajectory. So, whatever may be the requirement, this is a typical control system, because it is nonlinear and also it is a benchmark problem. So, the R-TAG system, consider the following example: rotational translational proof mass actuator R-TAG. The R-TAG system combines a translational oscillator with a rotational proof mass actuator. Okay. So, this portion, this particular portion oscillates, okay, by the action of the spring. So, this is called combines a translational oscillator. So, this oscillates in the x direction with a rotational proof mass actuator. So, this is rotation. So, the oscillator consists of a cart connected to a fixed wall by a linear spring. The cart is constrained to move in the x direction only. The proof mass actuator is attached to the cart and is controlled by an applied torque N. F is disturbance force that perturbs the cart. Okay. F is the disturbance force that gives as a disturbance input. The cart position and actual angle is xc and theta respectively. That is the cart which you saw here, this is xc and this is theta already, which I have already shown. So, mass of the cart is given 1.36 kg, proof mass is 0.096. So, that is the mass of this cart is m and proof mass is small m. So, small m is 0.096 kg, distance of the link length of the pendulum is 0.059 meter, moment of inertia of the proof mass is I is 0.00022 kg meter square, spring constant K is given 186.3 Newton per meter. So, now we define some normalized variables which is zeta is xc root over m plus m upon I plus ml square, tau is t, k upon m plus m, and u is, this is my actual input, and m plus m upon k into 1 minus m l square, k is the spring constant, and omega is 1 upon k m plus m by I plus m l square f. Okay. So, given that, you see that we can write we can derive the dynamics of the RTEC system. You can easily see that it has 4 states. X1 is zeta, is actually representative xc normalized. This is xc dot, the velocity of the kite normalized, which is x2, and theta is the pendulum angle, x3, theta dot is the angular velocity of the pendulum, which is x4, and control variable is u, which is also normalized, and the torque, and disturbance is w. So, disturbance is w, this one w is this disturbance. Okay. So, if you look at, so x dot, this is a 4th order system, and the expressions are x dot equal to x2. So, advantage is that we have not kept any parameters associated, the simplified x2, you can see x dot is in this, this I can say this is simply a function of x, this is another function of x, maybe gx, I do not remember what I have said, yes, gx, and this is dx. Okay. So, you can say this is a function vector with 4 dimension, function vector with another 4 dimension, and another function vector with 4 dimension. So, this is my so you can see that system is highly nonlinear. Epsilon is defined as ml upon root over I plus ml square into m plus m. You can easily derive this equation. I will not discuss further on this. So, all that I am trying to tell you that RTOC system has a nonlinear dynamics, which is type x dot is fx plus gx plus gx into u plus dx into w, where w is the external disturbance, u is the actual control input. So, the Fuzzy-Lyapunov synthesis of RTEC, the system dynamics now can be written as we said, x dot is fx plus gxu plus dxw. Without knowing fx, gx and dx, following linguistic statements can be formulated. Even if I do not know what is fx, gx, dx exactly, but I can still write the state of the system is described by x1 the cart's position, x2 is equal to x1 dot, and x3 is the actuator's angle, and of course, x4 is x3 dot. So, that is x3 is theta, x4 is theta dot, x1 is xc normalized. Okay. So, x1 is xc normalized, okay, and x2 is x1 dot, and this is another important thing that I can easily tell you. x4 dot is proportional to the control input u, that you can easily see here, because you see that this is my pendulum, and if I assume that there are no friction and other things here, then my pendulum, the acceleration of this pendulum, angular acceleration obviously is directly proportional to the torque applied n, and since my input u is normalized value of n, and hence I can always say that x4 dot, the acceleration of the pendulum is proportional to the control input u, and similarly x2 dot, the velocity of the kite is proportional to negative of x1. You can easily see that because the spring is connected. So, it is like this spring, and this is the block max. So, you see that x2 dot, the velocity is always because of spring action, it will be always in this direction, the velocity. Okay. So, if I move x in this direction, x2, so the position if in this direction, the velocity is in the negative direction. So, x2 dot is proportional to minus x1. The control objective is to find u such that the system is stable around x equal to 0. So, this is the regulation problem. So, let V is half x 1 square plus x 2 square plus x 3 square plus x 4 square be the Lyapunov function candidate. Then using S 1 the assumption that we have 4 states, V dot is x 1 dot and x 1 dot is x 2. Similarly, this is 2 x 2 dot. So, x 2 dot plus x 3 dot and x 3 dot is x 4, and similarly this is x 4 into x 4 dot. So, before this is the second step. The first step V dot, if you look at here, is x 1 dot plus x 2 dot plus x 3 dot plus x 4 dot. So, because we know already that x 2 is x 1 dot and x 4 is x 3 dot. So, this second step comes. So, now you see that we have already said x 2 dot is proportional to minus x 1. So, obviously qualitatively if I put x 2 dot is minus x 1, these two terms qualitatively cancels out, whereas only these two terms remain. So, x 3 x 4 is remained, and then I know already that x 4 dot is proportional to u. So, I can put this x 4 dot instead of x 4 dot I put u. So, you see that what is the advantage here is that I am designing a rule base, but while designing rule base I am not utilizing the system dynamics. Okay. So, I am finding out what is V dot equal to x 3 x 4 plus x 4 u. While I am finding this expression, I am not using the system dynamics. This is very important, kindly give attention, pay attention to this. System dynamics is not used. What is used? The simple physics. The simple physics of the system is that here we used x 2 is equal to x 1 dot, obviously the velocity x 2 and x 1 is position, and similarly here we use the notion that the x 4 is x 3 dot. So, x 4 is theta dot and x 3 is theta, which is very simple. And also we used other two from the systemic connections. We know already the acceleration of the pendulum is proportional to the input, and x 2 dot is proportional to minus x 1 just by constructional feature. So, using these two rule we found V dot to be qualitatively x 3 x 4 plus x 4 into u. Okay. So, now even if we do not know the system dynamics, okay, but looking at this we can create a rule base for which this V dot can be qualitatively negative definite. So, classical Lyapunov synthesis suggests that design of u that will guarantee V dot is negative definite. Same idea is applicable here, but in the domain of computing with words, means this is qualitative, not quantitative. So, what we are trying to do, we are applying the Lyapunov synthesis to the system dynamics, partially known system dynamics for generation of rule base. So, now we take the example when I say, so we derived V dot equal to approximately qualitatively x 3 x 4 plus x 4 into u. So, this can be made negative definite if the rule base is formed as follows. You see that I will just take I will take care that you understand this, because this is the this is what you should learn, how to generate a rule base. You see x 3 is negative, x 3 is negative. If x 3 is negative and x 4 is also negative, so that means this quantity is positive. Now, x 4 is negative, and if u would become negative, then this whole thing is positive. So, no way you can make the system stable. So, obviously the rule base should be u to be positive. So, that is what is the rule. I am again repeating, if x 3 is negative and x 4 is negative, in that case x 3 x 4 is positive. So, x4, this implies x4 into u should be negative. To make these two quantities to be qualitatively negative, because we want to make these two quantities to be qualitatively negative. So, x4 u should be negative, x4 is already known as negative. So, u has to be positive. So, this is the first rule. If x3 is negative and x4 is negative, then u is positive. Similarly, if x3 is positive and x4 is positive, so x3 is positive, x4 is positive means again x3 x4 is positive in this case, and this implies again x4 and u should be negative, and since x4 is positive, so u has to be negative, which is negative. So, then the second rule is if x3 is positive and x4 is positive, then u is negative. I hope you are able to follow what I am trying to say, I am presenting you. So, if now let us see the other possible combination. If x3 is negative and x4 is positive, so in this case x3 x4 is negative. So, if x3 x4 is negative, so I must ensure that x4 u. Since it is already negative, so this should be 0 is sufficient. If I make x4 u 0, because x3 x4 is negative, is very good. Okay. So, this is simple, because there are other ways also. If x3 x4 is negative, I can say x4 u is also negative, much better, right. But this is the simplest one, x4. So, x3 is negative and x4 is positive, then u is 0. You can also think another possibility, u is, because x4 is positive, so u is negative. This is also possible. Similarly, if x3 is positive and x4 is negative, so then again x3 x4, in this case x3 and x4 sorry x3 negative, x3 is positive and x4 is negative. So, x3 x4 is negative. So, this implies, so you can make x4 u is 0 or x4 u again negative. Okay. So, since x4 is negative, so u is 0 or u is positive. But in our in this case we have only considered this 0. So, I wish that this is the most important part of this lecture, that how do we, first of all, using partial knowledge of the system and without taking the help of system dynamics, we first of all found out the rate derivative of the Lyapunov function is approximately qualitatively equal to x3 x4 plus x4 u. And using this expression, we computed a set of rule base such that B dot can be negative definite. So, what we have not until now found out in this is the parameters negative, what are the parameters associated with negative. Okay. So, if I am assuming this Fungi linguistic variable to be Gaussian functions, okay, which we have taken in this case. So, Gaussian function is normally represented by two parameters, one is mean, another is sigma. So, if I say sigma is 1, then these linguistic variables, they are all represented by one parameter, that is the mean, and the u is positive or negative that we have defined here, we have taken them to be singleton. So, standard Gaussian membership function are used to define the linguistic term in the rule base as mu positive of x is e to the power minus x minus a x whole square. This is the parameter that we have to identify. Similarly, mu negative membership function of negative of the variable x is e to the power minus x plus A x whole square, okay. And mu z x is 0, x is e to the power minus x square. So, A x is the represents mean, x stands for state variable, p and z denotes the positive, negative and 0 respectively. Using the product for AND inference and center of gravity method for defuzzification, the fuzzy controller is given as, we have 4 rules. So, for 4 rules, the u, if you look at here, what I will do is that in this I find out the membership function of this, So, this is mu x 3 into mu x 4. So, that is the membership function for the my control action, and this is a fuzzy singleton which I define as a u, which is defined as a u, okay, the fuzzy singleton. My control action is a u. So, mu negative x 3 mu negative x 4 into a u is the output of the first rule, So, here again to let you know, I again explain here how we are actually doing this. I do not have to do everything again, you can easily understand. So, what is control action from this rule base? Obviously, I find out what is mu n x 3 and mu n x 4, the membership function of this, into u is positive and it is a singleton, and so that is why this is a u. So, a u is the singleton value associated with this control action a u, simply multiplied. So, this is the output of this controller. Similarly, you can easily see the output of this controller, output of this rule base, this rule, and the second rule output will be mu p x 3 into mu p x 4 into, this is a negative, so minus a u, okay. So, that is what we are doing here. So, mu n x 3 mu n x 4 a u mu p x 3 mu p x 4 minus a u. I will not even consider this because we are assuming, just you see that this is 0. If I simply say the control action is 0, because control action is 0 is sufficient for me to make this rate derivative to be negative definite. So, simply making that, what advantage I am gaining is that I am not reducing the parameters that has to be optimized or heuristically that has to be tuned. Okay. So, this is my control action. So, by center of gravity method, you just add all these individual membership function associated with the control action. So, there are 4. So, and finally, you get the value by taking mu p x is e to the power minus x whole square, and mu n x is e to the power minus x plus a x whole square. We can write u to be this function. Okay. So, this is your control. This has nothing to do, you can, because we have taken a Gaussian function. So, finally, you can simplify this u, but you also you can take any other functions, triangular function or whatever function you want liked. But if you look at this control action, what are the parameters that you do not know? This is, one is a u, another is a x 3, another is a x 4. Okay. All other things x 3, x 4. So, these quantities that you are getting feedback from the system. So, these 3 parameters, they have to be found, and we can do any kind of optimization algorithm, and particularly we have used genetic algorithm, particularly univariate marginal distribution algorithm, univariate, this is wrong here, univariate. We have already described in the previous classes what is univariate marginal distribution algorithm. So, this has been used to minimize this cost function, and by minimizing that, the optimal parameters are found to be the mean of the linguistic variable for x 3 is 0.73 and for x 4 is 0.25. This is either positive or negative. So, when negative is just, so that this is the mean, and AU, the control action singleton, is 1.4. So, this was done. So, this design is over. Now, we can simulate the system, which will show the results at the end of the section, but here before that I will derive again another kind of rule base for the same system. So, the u instead of earlier case u was simply a linguistic variable, but now I am assuming this is a state variable technique, where u is minus k 1 x 3 minus k 2 x 4. Of course, this is just to simplify, but actually I should have taken all the x 1 x 2, I have not taken, just to simplify, because if I am able to control using only 2 variable, I can only expect that using x 1 and x 2 I can improve the performance. So, putting the expression of u in v dot is already, we have found out this earlier, so because we are considering the same RTUC system. So, for RTUC system, given the physical principles, v dot qualitatively comes out to be x 3 x 4 plus x 4 u. Now, this v dot can be written as x 3 x 4 and then x 4 u is this quantity, which is minus k 1 x 3 minus k 2 x 4, and this can be again simplified, which is 1 minus k 1 x 3 x 4 minus k 2 x 4 whole square. So, how do I now derive the rule base for this kind of structure? So, I just have to make sure that I have to select k 1 and k 2 in such a way that this quantity is negative definite. So, this is what, if x 3 is negative and x 4 is negative, then u is so you see that x 3 is negative and x 4 is negative. Okay. So, this quantity is positive. Since x 4 is negative, so the x 4 square is positive. So, all that I have to make sure that 1 minus k has to be negative, as well as k 2 is also negative, positive. So, k 2 is positive, and 1 minus k 1 is, because this is positive, so this has to be negative. So, 1 minus k 1 is negative, means k 1 is greater than 1. So, you see. So, this is my first rule. Second rule is, if x 3 is positive and x 4 is positive, so this quantity is positive, this quantity is positive. So, to make it again negative definite, so again I will have the same principle, whatever I got here I must get that. So, k 2 p p is greater than 0, k 1 p p is greater than equal to 1. Same condition, only this n n stands for the rule base when x 3 is negative and x 4 is negative, and here p p stands for x 3 is positive and x 4 is positive. So, this in the second second rule, you saw that the same condition came, but these are different parameters, you have to remember k 1 p p. So, if x 3 is positive and k x 4 is positive, then u is u equal to minus k 1 p p x 3 minus k 2 p p x 4, where I showed you that this has to be positive and k 2 has to be negative, positive. Now, let us go to the third one, x 3 is negative and x 4 is positive, then u is minus k 1 n p x 3 minus k 2 n p x 4. So, how do I find out what is k 1 and k 2? So, it is simple, k 1 n p, you see that x 3 is negative and x 4 is positive here. So, that makes this is negative. So, this is negative, means this has to be positive. So, k 1 1 minus k 1 has to be positive. Okay. So, k 1 should be less than 1. Okay. So, that is k 1 n p is less than 1, and here this has to be again positive quantity k 2 x 4, because this is negative is already there. So, x 4 is positive. So, this is always positive whether x 4 is negative or positive. So, to make it negative sorry positive, K 2 also has to be positive. So, this is what K 2 N P, okay, this has to be positive. Similarly, if x 3 is positive and x 4 is negative, so again this is negative. So, this has to be again positive. So, again K 1 should be less than 1. So, K 1 P n is less than 1, okay. And K 2 P n, K 2 P n is a has to be, again here you see this is always positive. So, K 2 has to be always positive. So, you can easily see that this K 2 always in every case is positive, only in this case in the beginning in the first one it was positive and the second it is negative. So, what you got an idea that what should be this value K 1 and K 2, okay, at least the magnitude you know. Now, heuristically you have to tune these values, what should be K 1 N n, K 2 N n, K 1 P p, K 2 P p, K 1 N p, K 2 N p and K 1 P n and K 2 P n heuristically, or I can use a genetic algorithm, or we have done that univariate marginal distribution algorithm to optimize this parameter. So, you see that considering the same membership function and using product and end inference and center of gravity method for defuzzification, the fuzzy controller is given as like this. Okay. Since mu p is this and mu n is this, which we have already done in the previous case, we can write u as like this is a controller, and by simplifying that, so we have actually 10 parameters to be identified. So, 2 parameter x 3 x 4 the mean for linguistic variable x 3 positive, for x 3 positive and x 3 negative the mean is a x 3, and for but actually in case of one case mean is positive and case of mean is negative actually. So, that is what we are doing, that when it is negative mean is negative. Okay. So, the sign changes, that is why you saw that here in this case this is positive x, when it is negative mean is negative. So, it is positive quantity and mean is positive here in case of positive. So, it is negative here. So, a x 3 is 0.25 by doing optimization using univariate marginal distribution, a x 3 is 0.25 and a x 4 is 0.12, and the parameters, the controller parameters, that is K 1 and K 2 for all the different fuzzy rule, 4 rules are there, and for each rule we have 2 parameter K 1 and K 2, and we have got these values 1.2, 1.4, 0.6, 0.8, 0.35, 0.2, 0.4, 0.25. So, this is this parameters we derived using univariate marginal distribution algorithm. So, you see that simulation results x 1 converges to 0 with time. So, what we started with, we gave some initial disturbance and using the initial disturbance we are showing now here x 1, the x 1 is the position of the cart. Okay. You give some little disturbance to the cart, finally, it should come to the rest position. So, what is meaning of PD? This is the FLC controller we have used the PD type of rule base, that is if x 1 is x 3 is positive and x 4 is positive, then u is negative in that kind of rule base. Okay. So, this is PD is actually the rule base that we formulated. So, this is we are denoting, we are saying this is PD, and this we are saying state feedback, because you see that u is a function of states. So, doing that you see that we have got the response that so this is in the second unit. So, after 40 seconds almost the oscillation comes to an end. and here x 3 is plotted, which is the angular position. Okay. That also should come to because the cart was disturbed. So, that although the pendulum was in the beginning initial position, but it will start oscillating, and that oscillation will gradually slow down, and in equal same amount of time this has reduced to 0, both the PD type of rule base and state feedback type of rule base. Okay. And this is the control action, and in this control action you see that the control action is also fairly smooth, both for PD as well as state feedback. So, saying that what we did is that we did the regulation, that is, given the RTOC system, we gave some disturbance, and we showed that this controller is able to stabilize the system. Now, the tracking controller, that we would like that our pendulum should track a desired trajectory. So, for tracking a desired trajectory, what we would like to have is that instead of the Lyapunov function, which we had half x 1 square plus x 2 square plus x 3 square plus x 4 square for regulation problem, now we will consider u 1 square plus e 2 square plus e 3 square plus e 4 square be the Lyapunov function, where E I is desired state trajectory minus the actual state trajectory. So, x I is the ith state and x I d is the corresponding desired state trajectory. Okay. So, the control objective is to find a control action such that the actuator angle will follow any given desired trajectory. Hence, the Lyapunov function has been changed from x 1 square plus x 2 square plus x 3 square plus x 4 square to, in this case, e 1 square plus e 2 square plus e 3 square plus e 4 square. I hope that is clear to you. So, now in the same manner we can show also E I dot is x I dot d minus x I dot is same as x I plus 1 d minus x I plus 1, which is E I plus 1. What is x I plus 1? Because you see that we have the parameters which is x 1, x 2, x 3, x 4. Okay. So, when I say x I 1 plus d, when I say x I is this is x 1. So, x 1 dot d is same as, so this meaning x 1 dot d is same as x 2 d, obviously, because x 2 and x 1, the relation is x 2 is x 1 dot. So, by that principle you are able to see that x I dot d is x I plus 1 d, which I am writing here. And similarly also I can write x 2 x 3 dot d is x 4 d, okay, x 3, because x 3 dot is x 4. So, obviously x 3 dot d desired is x 4 desired. Okay. So, for I equal to 1 and 3, that is what I have done, I equal to 1 and 3, and differentiating V, we get V dot is E 1 E 2 plus actually this is E 1 E 1 E 1 dot, E 2 E 2 dot, E 3 E 3 dot, E 4 E 4 dot. So, we already know what is E 2 is E 1 dot, and this is retained, and E 4 is E 3 dot. So, this is our actual expression of E 1 dot, and just like again x 2 dot is approximately minus x 1 and x 4 dot is approximately u. Thus, in the same similar logic we can simplify this V dot to be qualitatively E 3 E 4 plus, because qualitatively this will cancel out this, because U 2 E 2 dot would be minus of E 1. So, this will be cancelled, cancelling out qualitatively. So, what is remain is E3 E4 plus E4, and for E4 dot we see that X4 dot is directly proportional, sorry, X4 dot, this is not right, X4 dot is directly proportional to U. So, we can you can write that this is E4 and E4 dot is V, where V is X4 dot D minus U. Okay. So, this is very simple because E4 dot is X4 dot desired minus X4 dot, and since this is X4 dot, I put this X4 dot to be U, I can replace that by U, and X4 dot D minus U I can write V, and that V is X4 dot D minus U. Okay. So, what we have to do now, I can create a rule base from this Lyapunov function, assuming V to be my control input, and from V, if I know V, then I know U, actual control action, this is pseudo control action, my actual control action would be X4 dot D minus V. So, in general what we learnt is that for regulation the qualitative equation for rate derivative of Lyapunov function was x3 x4 plus x4 u. For tracking we found out this to be x4 v dot is qualitatively equal to E3 E4 plus E4 into V, where V is x4 d minus x4 dot x4 dot d minus u, and u is the actual control action and v is the virtual control action. So, the v can be designed in the same way as that of u in the regulation problem. So, I will not be going in detail this because this and this has same structure. So, the rule base either using the PD type of controller or the state feedback type of controller, the rule base, the two rule base will have same form. Only thing that I am computing now V. After I compute V, so V will have the same structure that we earlier derived the same way, but given V I find out u to be x4 dot desired minus V. So, doing that, and also the parameters, in the first case we will have 3 parameters, in the second case similarly 10 parameters that have to be optimized. So, by optimizing these parameters we get, this is AV not AU, AV is 1.5, AE3 is 1.23, AE4 is 0.55, and for the tracking controller 2 you have these parameters 0.37, 0.26, and these are the parameters for the state feedback controllers for 4 rules. So, K1 NN is 1.3, K1 NP is 0.9, K2 NN is 0.6, K2 NP is 0.45, and so on. So, given that the tracking results is x3 is plotted against time, desired PD and state feedback, PD and state feedback give the same result here for the tracking. You see the tracking is not as proper because you see that the rule base is very small that we have taken, and also we have in the state feedback controller also we have rejected in the state feedback the input of x1 and x3, the state feedback of x1 and x3, x1 and x2. So, there is the tracking here is not right, there is some large error here, otherwise tracking is proper. And the control action you can see both PD and state feedback they behave almost similarly. So, finally, the summary, in this lecture the following topics have been covered. A classical Lyapunov synthesis method is extended to domain of computing with words, that means qualitatively how can we use the rate derivative of the Lyapunov function in such a way that the rule base can be generated. This new approach is used to design two different types of controller, actually the two different types of rule base. Controller is same fuzzy logic controller Mamdani type. Rotational proof mass actuator system is presented for simulation. Assuming minimal knowledge about the system, we have systematically derived the fuzzy rules that constitute the rule base of the controller. Using rule based controller, we have designed for both regulation and tracking purposes. Simulation results are presented. References in this case are some of the related papers are, you can easily see, fuzzy Lyapunov based approach to design the fuzzy controller, fuzzy sets and system in 1999 by Margaliot and Langholz, and same author also have a paper on fuzzy control of a benchmark problem computing with words approach IEEE transaction fuzzy system 2004, and also we have a paper, some work on this direction on intelligent control schemes for a redundant manipulator, presented in a conference held in Pune in 2005 December. Thank you very much.